Today we're going to be proving one of the sum and difference identities. These are all the sum and difference identities for sine and cosine. What we'd be interested in today is this one right here. Okay, and so our goal is to prove this. The motivation is that if we have something like the cosine of 15 degrees, we want to know the exact solution. A calculator can only give us an approximation. So I would expand 15 degrees into 45 minus 30, because 45 degrees is something we know what cosine and sine values are from the unit circle, and same with 30 degrees. We could have chosen any other values, but I wanted to choose unit circle values so that we can find exact values for the cosine of these things. So what we'll do is we'll call alpha 45 degrees and beta 30 degrees. And we can expand the cosine of 15 degrees using the right-hand side of this equation, like so. And at this point, we can pull up the unit circle and come up with the values of the cosine of 45 degrees. If you don't already have them memorized, here's the unit circle. We start here and we say here is our 45 degree angle, and cosine is the x coordinate. So we know that the cosine of 45 degrees is the square root of 2 over 2. Then we go to 30 degrees. And we take the x coordinate because that corresponds with the cosine of 30 degrees is the square root of 3 over 2. So we're going to multiply the square root of 3 over 2 by the square root of 2 over 2. Now we have the sine values to take care of. For sine, we use the y coordinate. So here at 45 degrees, the y coordinate is the square root of 2 over 2. And we add the square root of 2 over 2 in there. Then we take into account 30 degrees, the y coordinate is 1/2, filling that in. Now, we could be done here, but sometimes it's a lot nicer to simplify this. Notice both terms have a square root of 2 over 2. If we factor that out, we'd be left with a square root of 3 plus a square root of 1. We factored out the square root of 2, and we consolidated the denominator to 4. And so this is the exact solution of the cosine of 15 degrees, right here. No approximation necessary. Now, what are we going to do to prove that this works? Now that we know why we want it, how do we prove that it does work? And it all comes from this unit circle. So on the unit circle, we have labeled the angle A, which is going to be our alpha, the angle B, which is going to be our beta, and the angle A minus B, right here, alpha minus beta. The first thing we need to do is come up with the points. Now we know that the points on a unit circle correspond to the cosine theta, comma the sine theta. So for P, we use the angle A. So we have cosine A, sine A. For Q, we use the angle A minus B. So we have cosine A minus B, comma sine A minus B. Then for R, we use B. So we have cosine B minus sine B. And then for S, it's on the y-axis. We use an angle of 0. And the cosine of 0 is just 1, and the sine of 0 is 0. So now we can place those points on our circle, or the coordinates for those points on our circle. Or what you might notice is that we have two triangles here. We have a triangle that is created by the radius connecting the center with the point P and the center with the point R. Now, this point P had the angle A, and this point R was created by the angle B. So the central angle in here from B to A is A minus B. So we have a central angle of A minus B for this red triangle. Q is created by the angle measuring from 0, right here, to A minus B. So its central angle is also A minus B. So we have two triangles. Now both of these triangles have a central angle of A minus B. Two of the sides of each of these triangles are equal because they're all the radius of the circle, or they're all unit 1. 1, 1. So all of these are length 1. The blues, the reds, everything's length 1. So these two triangles are congruent. That means that this side of the triangle, the third side of these triangles from P to S, from P to R, is equal to the length from Q to S. So we use mathematical notation for that segment, PR, or the magnitude of the line segment, PR, or the distance between the points P and R. So we need to plug in our values. I'm going to call point P our x2, y2, and our point R, our x1, y1. And I just erased something. Nope, it's back. There we go. So we're going to plug those values in for x2 and x1. So here we go. Here, if you remember that when you have two values, a minus b, and that quantity is squared, we can use FOIL and take a times a times negative b times a, and negative b times negative b. And simplifying that, collecting like terms, we get a squared minus 2ab plus b squared. So if we look at this first one, cosine A is our A, and cosine B is our B. So we're going to replace cosine B with all the B's, and all the A's are going to be our cosine A's. And so we're going to take this square root up here, and we're going to plug in the cosine A and the cosine B into their appropriate spots. And that's a typo. Let's use my pen, and we'll call that a capital B. There we go. Now we're going to do the exact same thing with the other side now. Now sine A is going to be our A, and we got another A right there, and our sine B is going to be our blue, or our B's. And so we're going to expand this right here. So sine B, sine A. And then we get this. And so here we have the cosine squared A, and we also have a sine squared A. So if we use the sine squared theta plus cosine squared theta equals 1, the Pythagorean identity, as long as these two angles are equal, sine squared plus cosine squared equals 1. So here I have a cosine squared A and a sine squared A. And here I have a cosine squared B and a sine squared B. So I can replace the yellows with a 1 and the blue values with a 1, which is what I do in the next slide. So again, we took cosine A squared plus sine A squared and replaced it with a 1. Then we took cosine B squared plus sine B squared and replaced that with a 1. There's no more consolidation right now. We can't factor anything else out. So we'll just collect the like terms, and we now have a more simple solution or equation for the distance between P and R. Now that we have that, we can look at the distance between Q and S. So to do that again, we write the mathematical term this says, or this means the magnitude of the line segment QS is equal to the distance between Q and S. And we use our distance formula. We plug in for Q, we have the cosine of AB minus 1. So that's where our cosine of AB minus 1 comes from. For the y terms, we have sine AB minus 0. So we're just going to have the sine AB quantity squared. We only are going to need to FOIL out this first term right here. So again, we remember that we have the cosine of A minus B as our A's, and the 1 as our B. And so plugging that in, it's a lot simpler. We have the cosine squared of A minus B minus 2A minus B plus 1. Then we have the sine squared A minus B. But you'll notice again, A minus B and A minus B. These are the same arguments. So we can use the Pythagorean identity again. And when we add those two together, it equals 1. So we have the cosine squared of A minus B, the sine squared of A minus B, that's equal to 1. And then everything else is left. See this other one right here, this one and this one, that still remained. And that came from the B squared value here. So now we just need to add those two ones together. And we have a value or an equation now for the distance between point Q and S. And we'll put that up there. So we have these two distances now. They are the distance or the line segments across from the central angle of A minus B. So both of these distances then are equal. Okay, so we set those two magnitudes equal to each other. So if we take the magnitude of those squared, these square roots go away, and now we just have these two equations set equal to each other. So the stuff underneath the square root sign are now equal to each other. And a little bit of algebra to clean this up. On both sides we have a plus 2. So what we'll do is we'll subtract 2 minus 2 from both sides, and the result ends up being a negative 2 cosine A minus 2 sine A sine B minus 2 cosine A minus B. Now here on the left hand side, both of these have a negative 2 factor. So if we factor that out, we'll be left with the cosine AB and the sine AB, both positive because we're going to factor out the negative with the 2. So when we do that, we have now the negative 2 on the outside and the other stuff on the inside. And the right-hand side also has a negative. So we're going to divide both sides by negative 2. Negative 2, negative 2. And here, these cancel. The negative 2 and the negative 2 cancel. And we can then now have the simplified equation, which looks exactly like this, except we have the angles as A and B instead of alpha and beta. Now, I write it like this just so that you know that we can go from this left-hand side form in its expanded form and consolidate it. That would be useful if we wanted to take something, an equation that looked like something on the left-hand side, and graph it. So it might be easier to graph if A were X and B were some shift. Or we may want to do what our motivation to begin with is to take an angle like 15 degrees and write it using unit circle angles. So either way, we can use this form. We can either use it to expand the cosine of A minus B, or we can use it to consolidate the cosine A, cosine B plus sine A, sine B.